I want to do a small fundamental exercise that I think will really help you fundamentally understand forces and moments and their differences and what happens with the objects that they're applied to. So I'm going to ask you to participate in this exercise. I'm going to be asking you several questions, and then I'm going to ask you to pause the video, and once you think you know the answer, just unpause the video and I will tell you the answer. So let's get started. Let's assume that we are somewhere far, far away in the universe, far away from the Earth, so there is no force of gravity. You simply have a rod that is tilted at a 60-degree angle, and in the center of this rod you have a center of mass. So right now there is no force applied to this rod, so it just exists there, it just hovers there. So now what I'm gonna do, I'm gonna apply a force to this rod, but to the location of the center of mass. So the question to you is, what do you think is gonna happen with the rod after some time? Where will this rod be? And at which angle this rod will be? So pause for a second. So the answer is that you have to look at the center of mass. The center of mass will only go in the x direction. It will not go in the y direction. It will only go in the x direction. And the rod will still be at an angle of 60 degrees. If we apply this force again, then after some time, again, the center of mass will only move in the x direction, but it won't move in the y direction. So the y direction would be up and the x direction would be to the right. So the rod would only move in the x direction, and it would still be at an angle of 60 degrees. But how about if now I apply this force like this? What's gonna happen with the rod? So the answer is that now the center of mass of this rod will move up and also along the x direction. So your center of mass will be here, but the rod will still be at an angle of 60 degrees. So the angle won't change. Okay? So again, if I apply a force here, then you already know the answer for that. The center of mass will only move in the x direction and the angle won't change. So it will still be 60 degrees. All right? And now if I apply a force like this, then I guess you already know what's gonna happen with the rod. The center of mass will move down and the rod will still be at an angle of 60 degrees. So this kind of motion is called translational motion. So the object is translated, the center of mass of the object is translating along some kind of path, right? But it's not a rotational motion. As you can see, the angle of the rod didn't change. Why? Well, because there was no moment, right? Remember, what is it what makes an object rotate? It's a moment, not force. You need to have a moment in order to change the angle of your object. And the moment, in this case, is 0. Because even though you have force, but this force is applied directly to the center of mass. And so, since moment equals force times distance, and then the distance is 0 because the force is applied right at the center of mass. So the distance is 0, and therefore moment is also 0. 0 Newton meters. And therefore, you only have this motion where the center of mass moves, but the orientation of the rod doesn't change. Essentially, you can have this kind of motion of the rod where the rod moves along some kind of trajectory, but the orientation of the rod doesn't change. It's at the same angle. Okay, but now let's do something more interesting. Suppose that I have another rod here, and initially that rod again is at an angle of 60 degrees, and you have the center of mass here, and I'm gonna apply a force, but this time I'm gonna apply it here. So what do you think is gonna happen with this rod in terms of the motion of the center of mass and the rotation of the rod? Don't worry about the specific angles, just think about whether the angles will decrease or increase or stay the same, and whether the rod will go up or down or only in the x direction. So the answer is, remember, the force only makes the rod accelerate, right? So this force is only applied in the x direction, which means the center of mass of this rod will only move in the x direction. It will not move down, it will not move up, it will only move in the x direction. However, now pay attention, you have a distance here, right? The distance which is perpendicular to this force. And that creates a moment, right? So you have force times distance. So you have some kind of moment. And what do moments do? They make bodies rotate. So now this rod, its center of mass will still be at the same height, but it will have a smaller angle. So instead of 60 degrees, it will be 45 degrees. Let's take another one. I apply a force, but now like this. And now this force vector is perpendicular to the rod. So what's going to happen with the rod now? So now, if you look at the force vector, it also points down. It has a component in the x direction, but also in the y direction. And so because of that, the center of mass will move down. But now you also have a distance here. So because of that, you also have a moment. And since you have a moment, the object will rotate as well. So because of that, this rod will be even at a smaller angle, let's say 30 degrees. And finally, if we take two forces and we're gonna apply one here and one here, only in the x direction. And so the distance to one of the forces is d, and the distance to the other force is also d. So actually the distances here are equal, okay? They don't look like equal, but they're equal. So what will happen with the rod now? The answer is that now the center of mass will move only in the x direction because both forces are in the x direction, and the rotation of the rod does not change. It will still be 30 degrees. Why? Because even though you have one moment from this force, but another moment is caused by the other force in the other direction. So this moment here will try to make the rod rotate in this direction, but the downward force will try to make the rod rotate in this direction. And so because of that, both of these moments, they will compensate each other, and the body will not rotate. So you will end up being in this position where the center of mass only goes in the x direction, but the rod stays at 30 degrees. Okay, so I hope you've enjoyed the exercise and now you understand the moments and the forces. Welcome back. Here I have a truck with a crane, and the crane itself is 20 meters long, and we measure it from this point O until this point B. The angle of this crane with respect to this horizontal line is 30 degrees. The cable that goes from the roof of the truck through point B until point A, it experiences a 4 kilonewton tensile force. And also this point O is 1.5 meters above the ground. And now your objective is to create maximum moment about point O with this 4 kilonewton force. For that, you have to determine the horizontal distance from point O till point A. So you have to find this x that would give you a maximum moment about point O. And once you have it, you will also have to calculate that maximum moment about point O. So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's solve this problem now. First of all, let's find this distance x from point O to point A. And of course, we are only interested in the horizontal distance. Remember, this distance x needs to maximize the moment about point O due to this force P equals 4 kilonewtons. Essentially, you have your force and the distance from point O till point B, which is 20 meters. And now, question. What angle do you need to have between the force P equals 4 kilonewtons and the crane to make the moment maximum? Well, remember, if this is your crane and this is your force, then only the perpendicular component of the force to the crane will create a moment about point O. So let it be P perpendicular, and then this crane, that's your moment arm, and so you have to have 90 degrees here. And then the force component parallel to the crane does not contribute to the moment. And the same thing in this scenario. This is my crane, this is my force P, here I have 30 degrees, the crane is of course 20 meters long, and again I will decompose this force where one component is perpendicular to the crane and the other one is parallel to the crane. And if I want to calculate the moment about point O, then I have to pick this P perpendicular. That's because this P parallel does not contribute to that moment. It's parallel to the crane, so it doesn't create the tendency of rotation. And so in both cases, your moment would then be P perpendicular times 20. But obviously, your P perpendicular is smaller than your P force, which also means that P perpendicular times 20 is less than P times 20. Therefore, to maximize the moment about point O, you have to make sure that you have 90 degrees between the force P and the crane. And so with that, you can already calculate this maximum moment. Its moment about point O equals P times 20 or 4 times 20, which is 80 kilonewton meters, and it would be clockwise. And so that would be your maximum moment about point O. And now to calculate x, we will create this upper triangle here. So in fact, we have a right triangle here. This is the hypotenuse here. Then this side is 20 meters. You have 90 degrees here. And this is the third side. We can have alpha here. And we can calculate this third angle alpha like this. Alpha equals 180 degrees minus 90 degrees and minus 30 degrees. That's 60 degrees. And now you have the same angle between the cable and the ground. Using the sine rule, I can calculate this hypotenuse of this right triangle. It would be C over sine 90 degrees equals, and then 20 over sine alpha, which would be sine 60 degrees. So this 60 degrees, it's this alpha here. From that, I know that C equals 20 over sine 60 degrees, because sine 90 degrees, it simply equals 1. And so if I calculate that, then I will have 23.094 meters. But that's not exactly x, because point O is at 1.5 meters from the ground. So in fact, I have another small right triangle here in the corner, and I have 90 degrees here. Let me draw it here. So I will have alpha here, 90 degrees here, alpha is 60 degrees, and since the sum of all the angles inside a triangle must be 180 degrees, that means that this one here, that's 30 degrees. Then I know that this side is 1.5 meters, and now I have to find this side here. Essentially, you can see that it's x minus c. You have x meters here, you have c meters here, so this is x minus c. And again, the sine rule will help me. Remember, alpha equals 60 degrees, so I will have 1.5 over sine 60 degrees, it equals x minus c over sine 30 degrees. So x minus c equals all that. And that means that x equals this term plus c. And remember that this c here, it's 20 over sine 60 degrees. So x can also be written like this. In other words, x equals all this, which is approximately 23.96 meters, or even more approximately 24 meters. And that's your answer. X equals 24 meters, and this x will create the maximum moment about point O with this force, and this moment, MO, it's 80 kilonewton meters clockwise. Thank you very much. Welcome back. We have a crane here with all the necessary dimensions. The height of the crane from point A till point B, which is right here, that's 23 meters. The crane is lifting the load up at constant velocity. The mass of the load is 2 megagrams. Then the part of the crane from point B till point D, its mass is 1.5 megagrams. And the center of mass of this BD part is this point here, G1. Then the part from B till C, its mass is 0.5 megagrams. And its center of mass is this point here, G2. And then there is a counterweight here. It's a big heavy block, and its center of mass is this point here. We call it G3. It's right here in the middle of the block. The mass of the counterweight, it's 6 megagrams. And so the first question is, what's the resultant moment or the net moment about point A that is produced by this load, then by this BD part of the crane, then by this BC part of the crane, and by this counterweight. What's the resultant moment about point A? Then, what's the resultant moment about point B? So this point here. Again, due to load, then the two sections of the crane, BD and BC, and then the counterweight. And then the third question is, if you want your resultant moment about point A to be 0 Newton meters, then what kind of counterweight mass do you need to have? So, in the third question, instead of 6 megagrams, you will need to find another mass for the counterweight in order to make this moment 0. So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now solve this crane problem. First of all, remember that the crane is lifting the load up at constant velocity. This is the load here. Here you have the cable. Here you have the other side of the cable. And here you have the hook. So I have mentally cut the cable here, in this region. And so this load had a mass, and in fact, let's just call it M sub L equals 2 mg. So it's the mass of the load. And this mg here, that's megagrams. And now because of that mass, the load has the force of gravity, M sub L times g. Now this g here, that's the gravitational acceleration. This g here, that was gram. And so this point here, that's the center of mass of the load. And now, since the velocity upwards is constant, that means that the force of gravity that the load experiences, the crane experiences the same force at the hook, because that's what the Newton's first law says. There must be a balance of forces in order to keep an object at rest if it was at rest to begin with, or to keep an object move at constant velocity if it was moving at that velocity to begin with. Imagine if the forces were not balanced and the load accelerated upwards. Then you would have this case. This is the force of gravity of the load, but then here you would have another force, and then your F would be greater than M sub L times G. So the crane would experience that force F down at the hook, which is greater than the force of gravity that the load itself experiences. And that, of course, would mean that the load would accelerate up, meaning that the time derivative of the velocity of the load would not be 0 meters per second squared. So the velocity would not be constant. In this case, in the first case, dv over dt equals 0 meters per second squared, meaning that the velocity is constant. And in this exercise, this is our case. Thus, the crane experiences M sub L times G at the hook as well. And now what was asked first was the resultant moment about point A, right here, and the resultant moment about point B, which is here. However, all the four forces of gravity that we are considering in our moment calculations, the load, the two crane sections, BD and BC, and the counterweight, they all point down. So the force of gravity due to the load points down, then the force of gravity of this section of the crane points down, and the same thing goes for this section, and the same thing goes for the counterweight. All these four forces, they point down. That means that the perpendicular distances between the lines of action of these 4 forces and points A and B are the same. Thus, you will have the same resultant moments about point A and point B. And so to calculate MRA or MRB, which will be equal to each other, we define that the counterclockwise moment is positive and clockwise moment is negative. Thus, we write, by default, counterclockwise is positive, MRB, which is also MRA, and it equals minus 2 megagrams times G meters per second squared times 12.5 meters. So that's the clockwise moment from the load. The mass of the load is 2 megagrams. You have it here. G is the gravitational acceleration, and then 12.5 meters. That's the moment arm from point B until this load. So you have 9.5 plus 3, which is 12.5 meters. And it's negative because it's clockwise. Then you have minus 1.5 megagrams times G meters per second squared times 9.5 meters. That's the moment due to this crane section B and D. The mass of this section is 1.5 megagrams. The moment arm from point B until the center of mass of this section, that's 9.5 meters, which is here. G again is the gravitational acceleration, and it's negative because the moment is clockwise. Then plus 0.5 megagrams times G meters per second squared times 4 meters. So that's the moment due to this section BC. The mass of this section is 0.5 megagrams times the gravitational acceleration times 4 meters, which is this moment arm here from point B till the center of mass of this section. And it's positive because it's counterclockwise about point B. And finally, you have 6 megagrams times G meters per second squared times 7.5 meters. That's the moment due to this counterweight. 6 megagrams, that's the mass of the counterweight, times G times the moment arm from point B till the center of mass of the counterweight. Now, minus 2 megagrams, which is here, that's actually minus 2,000 kilograms. Then minus 1.5 megagrams, that's minus 1,500 kilograms. 0.5 megagrams, that's 500 kilograms. And 6 megagrams, that's 6,000 kilograms. And of course, remember that G equals 9.81 meters per second squared. And so if you calculate all that, you will get 76027.5 Newton meters, or approximately 76 kilonewton meters. And it's positive, so it's counterclockwise. So that's your answer. That's your MRB, and also that's your MRA. And now, let's make our moments about point A and also point B 0 Newton meters. In order to achieve this 0 moment, we have to find the right counterweight mass. For that, I will keep the counterweight mass as an unknown variable. Let it be x. And so, MRB equals, I will just take this equation here on the right, but instead of this counterweight mass here, which is 6,000 kilograms, now I will make it x. And the net moment here, I will make it 0 Newton meters. And what I can also do, I can factor out my g's from all of my 4 terms. So I will have g times and all that. So this x here, that's my unknown. And of course, all that must equal 0. And so in the end, I will have x equals all that, and that will give me approximately 4967 kilograms. So the mass of the counterweight has to be 4967 kilograms, or 4.967 megagrams. Then the resultant moment about point B and point A will be 0 Newton meters. Thank you very much.